Greetings. The goal is to talk today about one-dimensional strain. So we're going to try and describe that in hopefully reasonable terms. So what we're trying to describe is 1D strain. Okay? So strain in one dimension. We're looking at this worm that's up here. Right, and you can think of this almost as the same as a number line, the type of number line you may have used in elementary school. There is an origin that is here. We've defined a point M that's in this position, and M is a distance x from the origin, right? And the origin is here on the left-hand side. So we take this worm, and we're going to stretch it one-dimensionally. We're going to stretch it in the x direction. It gets longer, and it also gets a little bit narrower or thinner, as you might expect when we stretch something. That's conventionally what happens to a material. So when we look at the stretched worm, we find that this distance, which may have been to x here, which is the initial position of M has now moved to here. We've now described it as M prime. So we've added x and a u distance on here. And let me get the right tool. A u distance on here. So this distance is x, and this distance is u. So x plus u gets us from the origin to M prime. Okay? What we've described when we did that is we described a displacement. Right? So we have displaced all of the points on the worm. In fact, we've stretched the worm to create more points. But we've displaced this point M to the new position M prime, which is, rather than being x distance from the origin, it's now x plus u. The challenge with the displacement is that if we started out with a different size worm, but we stretched the worm the same amount, or if we started out with a different point, if we started out with a point, perhaps a point G that was only here, right, the displacement of G to G prime would be different than M because the initial length was different. The initial length x was different. So the displacement depends on the initial length. If we wanted to describe to worms that were of a different initial lengths what the same strain would be, in other words, if there's a certain amount of stretchiness at which the worm would feel pain, right, depending on the worm's initial length, a longer worm might be able to would in fact be able to undergo a larger displacement than a shorter worm. In order to calibrate for that, we use the term strain. So the term strain allows us to actually do things and describe the condition, the amount of deformation or the amount of distortion, as being a certain quantity that's applicable no matter what the size of the object is. So whether it's 1 millimeter across or 1 meter across, the amount of strain could be the same. Okay? In order to do that, we can use the same example. We can use the example of a worm. In this case, we're going to define a point M and a point N, and the distance between those 2 points as delta x. That's the distance between M and N in the unstretched worm. When we go and we look at the stretched worm, we find M prime and N prime for that same stretch up above, and we can describe this new distance between M prime and N prime as delta x plus delta u. If we use that description as our mechanism for describing the strain that takes place, we can write a strain, and we'll, in this case, write the strain as the letter E, but you'll also see often that we use letter epsilon, or similar letters from other alphabets, right, as being delta U, right, over delta X. Or if we write this in terms of the conventional way to look at a line, we can write this as M prime, N prime, defined as the distance between the two, minus Mn as a line segment, right, described mathematically as Mn with a bar on top, divided by Mn, right, that initial segment length from here. So we have Mn, that segment, right, then becomes this new lengthened segment. That allows us to describe what we call the engineering strain, which is an approximation, in this case an approximation for a particular tensile strain that the worm is undergoing, right? So this is a tensile strain that the worm is undergoing, and that means that the worm feels tension. So in this case, this is the adjective, and in this case, this is the noun. Okay? And so this is, in fact, the engineering strain, so we'll put an ENG down here so everyone knows for sure which strain it is. We can also describe the engineering strain as being, if the initial length of the worm was L, we could describe this simply as delta L over L, right? And that in words would be the change in length, right? The change in L divided by the original L. Okay? So that's the engineering strain. Now the engineering strain itself is also an approximation. If we want to be able to compare particularly large strains, we have to go a little bit further, and we're going to look at just that definition. Here in a second, let me erase the screen for a moment and get a new pen up here. And we'll see if we can go for a different color. And we'll talk about the true strain. Okay? The true strain is conventionally described if we use E as a symbol. As I said, we can also use epsilon. We can make sure people know which strain we're talking about and say that we're describing the true strain. And the true strain is if we write an integral for the initial length, perhaps L sub I, and the final length, L sub F, right, of dl over L. So for whatever our line segment is, that gives us the log of LF over Li. Okay? Turns out, if you replace the terms and look at what I wrote just a few minutes ago, this also can be described as the log of 1 plus the engineering strain. And that actually describes, that's the engineering, that actually describes the connection between those two terms. So that's an example, that's the definition, that's how we define the strain. In this case, we define the strain in the x direction, so we might describe this as EX, or you'll also see this is described as the strain in the x direction for an initial segment of length x. In some cases, you'll see this described as what people think of the x-axis as the one axis, and so this might be the strain in the one direction, or it could be written also more precisely as the strain for the stretch in the one direction along the initial length in the x direction, where x is the first one of the three axes defined. In fact, we're going to describe axes. We're going to describe axes as x, y, z, or 1, 2, 3, where there's an equivalence between x and 1, y and 2, and the z and a 3. And that's one of the things we'll be talking about as we go forward, particularly when we want to describe multi-axial strain. Thank you.